Good morning. This is your stat sensei, Mr. Spensei, and we're going to do an assignment, class assignment for the normal distribution and the central limit theorem, illustrating both. So a brake manufacturer designed a new brake pad for long haul trucks. Repeated tests were conducted on long haul trucks transporting a load of 75,000 pounds at 70 miles per hour. The braking test showed that the new brake pad allow the trucks to stop completely in an average distance of 515 feet. That's important because that's telling me my mean is 515 with the standard deviation of 62.5. All right, so we have our population mean and our population standard deviation. What is the likelihood that a single long haul truck with the new brake pad has a braking distance between 545 and 605 feet? So this is a single, so we're not working with central limit theory. We're not working about the means. We're working about an individual. So we need to make sure that this is a normal truck. And it should have said, um, should have said that it's approximately normally distributed, which it does, right? If it wasn't normal, we couldn't do it because it's a sample size of one. But since we're talking about normal distribution, we can go ahead and do this. So we have a mean of 515. And we want to know 545, which is above it. We also want to know 605, which is also above it. So we're looking for this distance in between there, 545 to 605. And so this is going to be a normal CDF. Our lower bound is the 545. Our upper bound is going to be 605. Our mean is 515. And our standard deviation is 62.5. So lower, upper, mean, standard deviation. So let's go to our calculator and get that in there. Second vars, normal CDF, lower 545, upper 605, mean 515, standard deviation 62.5. And we end up finding this about 24%, so 0.2406. All right, and you need to have the picture, the calculator commands, and then of course the resulting probability. So what is the probability that a randomly selected sample of 15 long haul trucks in the study will have a mean stopping distance? So this tells me I'm using the distribution of the means, or CLT, because we're talking about the mean. Well, normally I'd have to have a sample size greater than 30, but my sample size is only 15. But I can still use it because they told us before that it's normal. Because it's normal, I'm still good to go. All right, so let's draw the picture. This is still 515. And we want to be 545 or more. And we're going to go all the way to infinity. All right. Because we're working with central limits theorem, this is going to be a z-test. So we're going to write that down because we're going to go stat test z-test. And the calculator is going to ask us for the mean, which is 515. It's going to ask us for the standard deviation of the population. And the standard deviation of the population we said was 62.5. So that hasn't changed. It's going to ask us for our X bar, and our X bar is 545. And then it's going to ask us for our sample size, and our sample size is 15, and we need the greater than sign. So that's the work that we need to show. So now we're going to go to the calculator and drop that in there. So we're going to go stat, arrow over to test, z-test pops up, and our mean in this case is 515. Our standard deviation, 62.5. Our X bar 545, our sample size is 15, and we need greater than highlighted, and I have that. And when we do that, we find out that there'd be a 3% chance. So 0.0315. All right, so we need to have the picture, the calculator commands, and of course the resulting probability for full credit. So the distribution of SAT scores is approximately normal. So they're telling us we have a normal distribution with a mean of 1051. So mean is 1051 and a standard deviation of 211. For the purpose of this exam, assume that the students at Somerset High School have the same mean and standard deviation as the population. So we're going to believe that it's the same for both the Somerset and the population. What is the likelihood that a randomly selected Somerset student who has taken the SAT score has earned between 1070 and 1240? So in this case, a randomly selected student. So this is one student. So in this case, we're not using CLT, We're just using a normal. All right. And they told us the distribution was normal, so I can use the normal. So we have the mean of 1051. And we want to know what the probability is between 1070 and 1240. So we're shading here. This is going to be a normal CDF. Our lower bound is the lower part of our shading, 1070, 1240 for the upper, mean of 1051, and a standard deviation of 211. Lower, upper, mean, standard deviation. So we're going to go ahead and go to the calculator. Second vars, normal CDF, lower 1070, upper 1240, mean 1051, and the standard deviation we said was 211. And we end up getting about 28%, so 0.2789. Once again, we need the graph, we need the calculator commands, and we need the resulting probability in order to receive credit. So the next one, what's the probability that the average SAT score of a random sample of 25 students? All right, so now we have a random sample of 25 students, and we're talking about the average. So average is another word for means. We're talking about central limit theorem. Okay, normally we'd have to have a sample size of 30 or more, but in this case, the underlying distribution is normal, so we're good to go with it. The mean is still the mean, 1051. And we want to know it has more than 1,000, so this is 1,000 down here. So it looks like this is should be over 50%. All right. Oh, excuse me. It says less. I shaded the wrong direction. So let me redraw that. So 1051. This is 1,000. And we're shading this way. This is going to be a stats test Z test. So we need to list all of our components. So first off, we're going to call it a Z test. The calculator is going to ask for the mean, which is 1051. It's going to ask for the standard deviation, which is 62.5. The next thing it's going to ask for is the X bar, which is 1,000. And then it's going to ask for the sample size, which happens to be 25, which is okay because the underlying distribution is normal, and we're going to need to use the less than button. So stats test Z test. The mean 1051, 62.5. The X bar is 1,000 and the sample size is 25, and we need to make sure we're less than. When we do that, make sure I have everything in there right. The X bar is not 100, it's 1,000. And I end up getting a very, very small value. I end up getting a -5, which means it's 0.0000225. That's what that value means. Now, we only go 4 places. So in our case, we would say it's approximately 0. All right. Okay, continuing on. The manager of a cultural pearl farm has received a special order for 2 pearls between 9.5 millimeters and 10.5 in diameter. From past experience, the manager knows that the pearls in the oyster have beds have normally distributed. That's important. So that means we don't worry about the sample size. With a mean of 8.5. So the mean is 8.5 and a standard deviation of 3. Assume that every oyster contains 1 pearl. What is the probability that a single pearl is too small to satisfy the size requirement? Okay, so we're dealing with a single pearl, so we're going to be working with a normal CDF because it's a single value. So normal CDF with a mean of 8.5. But the order was 2 pearls between 9.5 and 10.5. So we can't be less than 9.5. So we have to be at least 9.5. And they say too small. Well, too small would be this way. Anything less. We're shading down to negative infinity. So normal CDF, negative infinity is my lower. My upper is 9.5. My mean is 8.5. And my standard deviation in this case is 3. So lower, upper, mean, standard deviation. We're going to go to the calculator and drop that in there in the normal CDF, second vars, normal CDF, lower, -9 raised to the 99th power, upper 9.5, mean is 8, standard deviation 5.3. Make that sure that's a comma. Oh, excuse me. That's what was wrong. That's 8.5. The mean was 8.5 and the standard deviation is 3. 8.5. And we end up saying there's a 63% chance that the pearl is going to be too small, which makes sense because we're over halfway. Halfway is here, so we're over halfway, so it should be it's likely to be more than 50%. What's the probability that the average diameter of 5 pearls is greater than 9 millimeters? So here we're talking about average, so we're talking about mean or X bar, so that's the distribution of the means, and we have a group. Well, we normally would have to have more than 30, but in this case, the underlying distribution is normal, so we can go ahead and use the central limit theorem. So this is going to be a central limit theorem, which means we're going to be using a z-test. And we want to know the probability is greater than 9. Well, my mean is 8.5. We want to know greater than 9, which is shading this way, which is positive infinity. So the calculator is going to say, what's your mean? 8.5. What's your standard deviation? It's still 3 because it's the standard deviation of the population. What's your X bar? And you're going to say it's 9. We need it to be an average of 9 or more. Our sample size is 5, and we need a greater than. So that's the work shown. Let's go to the calculator. Stat, test, z-test. mean 8.5. Standard, stat test, z-test, mean of 8.5. Standard deviation 3. X bar 9. N is 5. And we need a greater than. When we do that, we find out that there's a 37% chance. 0.3726. I want to check that one more time just to make sure. That seems high to me. Stat test, z-test. Everything looks good. All right, so about a 37% chance. What's the likelihood that a randomly selected pearl meets the size requirement? A randomly, so this is talking about one. We're not talking about the average. So this is going to be a normal CDF problem. We'll go ahead and draw the mean first. Well, then we need to satisfy the size requirement. What was the size requirement? They said between 9.5 and 10.5. So that's 9.5 here, 10.5 here, because both are greater. Normal CDF, lower bound 9.5, upper bound 10.5, mean 8.5, standard deviation 3, lower, upper, mean, standard deviation. So second bars, normal CDF, lower bound 9.5, upper bound 10.5, mean 8.5, standard deviation 3, and we end up getting 0.1169. Again, this is all the work that we need to see. The picture, calculator commands, and of course, the resulting probability. All right, the last scenario. Beef ranchers sell cattle at auction. The more the cattle weigh, the more the rancher makes. While there are numerous factors that determine the weight of the cattle, the rancher can impact the size of the cattle by waiting until the calves are older and changing the quantity and quality and type of food the calves receive. One particular rancher has a herd of cattle in which the weights of his calves are normally distributed. That's going to be important because that's going to tell us sizes. The sample size won't matter. With a mean of 560 pounds and a standard deviation of 123. So mu is 560. The standard deviation is 123. What is the likelihood that a randomly selected calf from this rancher is ready for auction weighs between 480 and 525? So a randomly selected calf. So that means we're talking about one. So this means we're working with the normal. And we have a mean of 560. And this is 480 down here. And 525 is also below 525. I didn't give me much room to write it up there, but there it is. And that's what I'm looking for. So this is a normal CDF. Lower 480, upper 525, mean 560, and then a 123 for the standard deviation. Lower, upper, mean, standard deviation. We go to the calculator. Second bars, normal CDF, lower 480, upper 525, mean 560, standard deviation 123. And there's a 13% chance they're going to be that size or in that range. So 0.1302. All All right, 18 of the ranch's calves that are ready for auction were randomly selected and weighed. What's the likelihood that their mean weight? So we have a group of 18, and we're talking about the mean. So this is a chance to use central limit theorem. Our sample size is normally too small, but the underlying distribution was normal, so we can go ahead and use central limit theorem. So this will be a central limit theorem, which will mean we're going to be running a z-test. So with that said, um, the population mean, the mean is the mean is the mean. So our population mean is 560. And they want to know what's the probability of having more than 600. So that's our picture. And mean 560, standard deviation 123. They gave us that earlier. X bar, the sample mean. What's the probability of having a group of 18 that weigh 600 or more? Our sample size is 18, and we are shading off to the right. So stat, test, z-test, mean 560, standard deviation 123, X bar 600, sample size 18. And we find out that it's about an 8% chance. So 0.0838. All right, this takes care of this video. I appreciate you watching, and I hope to see you on the next one.